Alright, in this screencast I'll be going over the AROW algorithm as presented in the paper. And so this algorithm keeps both a vector u, like the perceptron, to use for predictions, and also a covariance matrix sigma of mu. I don't know that a covariance matrix is exactly the way to think of this. It's kind of like a confidence matrix. And so our updates are going to depend on this. If we're really confident about our vector, then we're not going to update it much in that direction. And so we predict a new, we predict a label for a new point using the vector mu. And if there's a positive loss, meaning that either we predicted the wrong label or we predicted the correct label but the margin wasn't large enough, then we update both mu and sigma to minimize this cost function, where the first term here is the KL divergence of the old normal distribution and the new normal distribution. The second term is a loss term, and the third term here is something that's going to, when we minimize, that's going to try and make sigma small, right? And then we've got two hyperparameters here, lambda 1, and lambda 2, which can be tweaked to balance trade-offs between the different objectives that the three terms are trying to achieve. Right, and so for the KL divergence here, in the KL divergence, you assume that there's one distribution has the correct probability and one has the incorrect probability. In this case, the old one has the correct probability, and this is the incorrect one. And so that means that things are going to be easier to calculate, because most of the stuff will be in terms of these parameters, which have already been picked. And so we'll have fewer terms that depend on the parameters we're trying to pick. So it'll be easier to minimize this. Now some intuition for what's going on here. The first term, the KL divergence between these two distributions, that's going to discourage changes in the distributions. In particular, it's going to discourage changing mu by too much and also changing sigma by too much. And in particular, if mu can't change much in directions in which sigma is small, because that would change the KL divergence a lot, right? If this is basically this distribution, right, then we could shift like that a fair bit, because there'd still be a lot of overlap. But if we shift this way, then there's very little overlap, which would create a very large KL divergence. So, yeah. Now the second term, this is the regular term, right? The term that tries to make you update mu in a direction more similar to x. If the margin is too small, because you can create a loss that is non-zero, or that is positive even when you get the correct answer. And the third term is trying to decrease sigma in the direction of x. And I think this kind of makes sense. The more points we have in the direction of x, the more confident we are, right? It's like we've got an average of more points in that direction. And so therefore we want to make the variance in the direction of x smaller, which is why we throw this term in. So we're trying to minimize this, which means we try and make sigma smaller in the direction of x. And in their paper, for the loss function, they use this squared hinge loss, which is basically this. So as long as your margin is big enough, it's just 0, right? Because then the maximum of these two terms, this one will be negative, and so you get 0. If your margin is not big enough, then, so either you predict the wrong label, or you predict the right label but not with a large enough margin, then this will be positive. Then this will be positive and squared. So the more wrong we are, the bigger this ends up being. So that's the squared hinge loss. Yeah. Yep. And we've got a YT in here. YT is the label. Okay. So I wanted to go over an example to make this real, to make what this is doing. And so I'm just going to shift over here a bit. Yeah, maybe we'll zoom out a bit so we can see everything. So let's say we've got our mu vector. It's supposed to, there, we've got a mu vector and it's supposed to point towards the blues, okay? So let's say our mu vector is in this direction. And then we take our first point, which is maybe here. And let's say that our margin isn't big enough, okay? We're going to need a bigger vector pointing more in that direction. And let's also say that for now, so I'm going to call this sigma. Really sigma is a covariance matrix, but I'm just going to show that so far it's the same in all directions and it's fairly large. And this vector is my mu. And so since my margin wasn't big enough, I'm going to do an update. And so far, since the covariance is same in every direction, we're just going to do an update in that direction. So we're gonna whoa. All right, so we want to do an update in this direction, and it depends on this parameter, how big it is, how big our update will be. We don't want to do an update that's too big, otherwise we're going to be pretty far away. So let's say that we do a little update in that direction like this. And so now we have our new vector, which is going to be, so maybe this was mu1, now this is mu2. Okay? And also, since we've done an update in this direction, we're going to increase the confidence in that direction, which means that this circle, before this was sigma 1, it's going to become something more like that. Now I'm assuming that this parameter is fairly large, so my confidence increased by a lot with just one update. In fact, I want to illustrate in the next step, I want to exaggerate this even more. So they say this becomes our sigma 2, where we're much more confident in this direction. All right, so now I want to have a look at what happens next. I'm just going to copy this so that we can have another version, which we edit separately here. All right, and so now we'll erase the old versions. I can erase the old vector, just keep the new vector, and I can erase this one point now. Now we've got our new confidence. Yeah. Okay, good. So now let's say we pick another point. I'm going to pick another blue point because I think it's easier to think about. So, okay, I'm going to pick this point. And let's say that still our margin isn't big enough, right? And so we're going to do another update. Maybe next we pick this point, the margin was big enough, so we didn't do an update. Then we pick this point, the margin was big enough. This should have the other label, so that's good. So we didn't do an update. Then we pick this point. Now we're going to do an update because the margin wasn't big enough. And so we know we want to try and do an update in this direction. So we want to try and go in this direction. However, because we're so confident in this direction, when we minimize this, there's going to be a really big cost from moving in that direction, left and right. There'll be a much smaller cost from moving up and down. And so what we're actually going to end up doing is we're going to end up moving more in that direction, right? An amount that isn't too big, so that we don't have too large a cost from moving up or down either. And so we're going to get our new, this will be mu3. Okay? So we don't necessarily make updates in the direction of the vector, because this vector has some components in the direction that we're very confident in, and some components in the direction we're less confident in. And so overall, our update will tend to be skewed towards the direction that we're less confident in. What else? Yeah, and then we'll change this. Now we're going to be more confident in that direction, and so we're going to have updated confidence interval as well, which I guess will be maybe a bit more something like that now, after changing it, decreasing it in that direction. So that's the basic idea, I think, of what this algorithm does. And I think it makes a lot of sense to keep track of the directions. Basically, we're keeping track of the directions that we've done a bunch of updates in, and so we don't update those so much anymore. The directions that we haven't done many updates in, we're going to update those a lot more, which I think makes sense. Cool. So those are some examples. Lastly, we move on to some calculations. So we want to minimize this. So we want to minimize this, and so what they did is they expanded the KL divergence and got all of this. And they also, up here we've got lambdas, right? Here you might notice that we've got these 1 over 2r's. They're the same thing. They changed their lambdas to 1 over 2r's. I don't totally know why. But let's move on. And as you can see, some of the terms depend on sigma, right? And some of the terms just depend on mu. This is mu t minus 1 and sigma t minus 1, so those are fixed. We're not minimizing with respect to those. So some of the terms just depend on mu, some just on sigma, and so we can separate and minimize them separately. So we'll have these terms together, and we'll have these terms together. And this term doesn't matter. I'm not sure what D is. What is D? Yeah, I don't know what D is. Let's ignore it. So we can minimize mu and sigma separately. And yeah, and so this, and so we can see this relates to what we did here. Because we got the sigma to the minus 1, we could imagine taking the difference in our mu's and decomposing it into a component parallel, into components parallel to the, I guess, the eigenvalues of this sigma matrix. And so the component in that direction, well, sigma is has a large eigenvalue in that direction. So when we multiply by sigma to the minus 1, this is fairly small, which means the cost will be small. The cost will be small to making changes up or down. Whereas in this direction, another eigenvalue, the eigenvalue is quite small in this direction, which means when we take this, multiply by that, any changes in this direction will tend to have a large cost, because this is sigma to the minus 1. So a small eigenvalue means the inverse matrix has a large eigenvalue, so we get a big cost to making changes in that direction, which is why we don't end up making a change in the direction of the point. We end up making a change skewed towards the directions where we have lower confidence. And then, yeah, here, this is just a loss, which we're, of course, trying to minimize. So that's what happens with mu. And then looking at the sigmas, well, I find this much harder to interpret. However, what we can conclude, because the mu and sigma can be separated and minimized independently, what we can conclude is that sigma is always going to decrease. It's always going to decrease. How do we know that? Well, obviously, minimizing with respect to sigma does not depend on the value of mu, right? There's no mu's or difference in mu's or anything. There's none of that in here, right? Which means when we minimize this, we would get the same value as if mu was held constant. And if mu was held constant, then obviously, if we kept sigma the same, then, well, this would be 0, the KL divergence, but there'd be a cost to this. And so to minimize, to do the best job of minimizing the trade-off between these two terms, obviously we would try and make sigma a little bit smaller to make that term smaller, which would make this term a little bit bigger, and there'd be some optimum. And so sigma would only get smaller over size. Sigma would only get smaller over time. Reflecting, which kind of makes sense, since we get, after we've kind of averaged over more points, we should become more and more certain of our values, and so future updates should not be as large. So I think I've pretty much covered it. I just want to go over a quick review of what we covered. So, oops, let's make this red. All right. So it's got a mu vector, just like the perceptron. It's also got a covariance matrix sigma, which is used to control how large our updates are. And we try and minimize this thing, which has a KL divergence term so that we don't make changes that are too big. It has a loss term so that when our margin is not big enough or we make the wrong prediction, we tend to update in the direction of the vector. And it has a term which encourages us to reduce this covariance matrix in the direction of our update. Yeah, and these hyperparameters, we can pick them to make this work really well. Now, yeah, so I think I pretty much went over that. And so I gave this example where initially our vector was in this direction. We picked this point, which means that we made an update in that direction because our covariance was symmetric. And then we became more confident in this direction, which is why here I drew this as an ellipse with a much smaller kind of variance in the horizontal direction than the vertical, to show that we're much more certain in the horizontal direction now after one update. And then we looked at another update with this new confidence, this new covariance matrix, and we did that for this point. And so we're going to want to make an update in that direction, except it's very costly to make updates horizontally, which is why we instead made an update a bit more in the vertical direction, because that's what would tend to minimize this. So without incurring too large of a cost here, we could lower the loss by making a change a bit more in the vertical direction. And then, of course, our confidence interval became, our confidence became a little bit greater in that direction, and so we got a sigma 3. And so that would carry on. Here I guess we had a very large value of lambda 2, which is why our confidence became so much greater so quickly. I think in general this would not be the case, that it would change that quickly. Yeah. And so then we looked at the actual calculations. You plug in for the KL divergence what it actually is. We noticed that the sigmas and the mu's those terms could be separated, which means we could minimize with respect to mu and with respect to sigma separately. And so, and this corresponds to exactly what I was saying here. We tend to make updates. The cost is greater in directions where we have a small variance, because small variance means sigma minus 1 has a big eigenvalue in that direction. So big cost for changes in that direction. So we make updates, like I said, and I think it's harder to just understand the sigma part of this, but since the sigma update doesn't depend on mu, and we know if mu is 0, then we would definitely decrease sigma in the direction of x in order to make this term smaller, with little cost to the KL divergence at first. And so we know that sigma always decreases. We always get more confident in the direction that we're making updates. Yeah, so that's it. I hope you enjoyed this screencast. Thanks for watching.